So the next feature of solutions that we want to talk about is solubility. How soluble are different substances in solutions, and how do you tell? So you can actually do the experiment in the lab, and what you'll find is that you'll have substances that are either miscible or immiscible. If substances are miscible, it means that they are mutually soluble in all proportions. So if you take ethyl alcohol or grain alcohol, which we drink, you can dissolve this in water no matter how much is added. They're fully miscible in each other. You could have 99% ethanol and you could have 1% water. The water will dissolve. You could have 99% water and 1% ethanol, and that will fully dissolve as well. It doesn't really matter what proportions you mix these in. They will always be miscible in one another. So most substances, however, reach a solubility limit beyond which no more substance can dissolve into the solution. And so for many solutions, this is the case. If you have like table salt, for example, sodium chloride, you can keep adding it to water and you'll reach a point where no more of the solid can go into the water. That is a maximum amount of dissolved solute that you can get in there at equilibrium. This is called a saturated solution. If you continue to add solid after that saturation point, no more of it can dissolve into solution. It'll just sit on the bottom and not be able to go in. So for example, there's a maximum of 35.8 grams of sodium chloride that will dissolve in a 100 ml solution of water at 20 degrees Celsius. The temperature is going to be very important because we're going to see that both temperature and pressure can affect the solubility of different compounds. So we have to indicate what temperature that we have. But if we continued to add any more sodium chloride under these conditions, it'll just going to sink to the bottom of the container and sit there. It won't be able to dissolve. It's a saturated solution. So a saturated solution is going to be in this state of dynamic equilibrium. So you still have molecules that are moving. So you've got your solid solute in there. Some of it's dissolving into the solution. And when that happens, some of it's also recrystallizing. So you've got equilibrium going on. The solution is not static or fixed, but you have both of these processes that continue to go on. They're just going on at equal rates when you've reached the saturation point. So we can define solubility then as the maximum amount of a substance that will dissolve in a given amount of solvent at a specified temperature. The temperature, again, is very important. So the solubility then of sodium hydrogen carbonate or sodium bicarbonate is 9.6 grams in 100 mils of water at 20 degrees Celsius. But for sucrose, 204 grams of sucrose will dissolve under these same conditions. So each compound is going to have its individual solubility in very specific solvent systems. So for each substance, you have to do the experiment and see how soluble the substance is. So we said that temperature can affect solubility. So temperature often has a very dramatic effect on solubility, but sometimes it's unpredictable, and so we can't make large sweeping rules about temperature. We can say that most solids will become more soluble as the temperature rises, while the solubility of gases in a liquid tends to decrease when you have temperature rise. So if you look at these things in this left-hand graph, this is the solubility of these different solids inside a water sample as you're increasing the temperature. And you can see that for most of these things, as you increase temperature, you're increasing the solubility of the solid. But that's not always true. Cesium sulfate, for example, is much more soluble at 0 degrees Celsius than it is at higher temperatures. Sodium chloride, it doesn't really change very much either when you increase temperature. It's already pretty soluble at even 0 degrees Celsius. You can see that typically the opposite is going to be true for gases. Carbon dioxide is a good example. So as you increase the temperature, carbon dioxide inside a solution is going to become much less soluble. This is a good example because we probably all drink beverages that have carbon dioxide that is placed into them under pressure. So our Pepsi, for example, or other carbonated drinks, has carbon dioxide that's actually been pumped into them to give them that fizzy nature. We notice that it's under pressure. Once we unscrew the cap, there's a fizzy release, and you can see bubbles appear right in the solution. That's the carbon dioxide escaping from the top of the liquid because the pressure is released. If you continue to heat up your Pepsi, so if it starts off very cold, you're going to have more carbon dioxide stay in that solution when it's very cold. As your Pepsi warms up, you'll notice that it goes flat, right? And when it goes flat, that carbon dioxide is going to escape from that solution. So the carbon dioxide becomes less soluble and is going to be released when you have higher temperatures. And that's typically true for most gases that are contained in a solution. So you can have some special conditions then. So we said a saturated solution is one that won't be able to dissolve any more of the solute, even if you keep adding it. So, but we know that solids typically are more soluble at higher temperatures than at lower temperatures. And so what you can do is you can form something that's called a supersaturated solution. So if you have a substance that is much more soluble at high temperature, like if we took glucose, for example, and we heat our solution up to, about body temperature, about 37 degrees Celsius, we're going to get a lot more glucose to dissolve in that solution than we would if we were at room temperature at about 20 degrees Celsius. So if we increase that temperature, we can increase the saturation point of glucose. If we then cool that solution back down to 20 degrees, we're going to have what's called a supersaturated solution. Much more glucose will be in that solution now at 20 degrees than there should be possible at 20 degrees. Almost double the amount of glucose would go in. And so these supersaturated solutions are going to be very unstable, and they can have dramatic precipitation reactions that can occur if they're disturbed. So even just shaking them sometimes can cause the supersaturated component to fall out of solution very quickly. So our supersaturated solutions are going to be unstable. When we're thinking about gases, this usually doesn't happen for gases because the addition of heat usually decreases the solubility of most gases. This can have pretty dire effects on wildlife. And so one of the major components that keeps fish alive is the ability of the water to hold the oxygen gas, right? Because the fish actually are breathing through the water. They need to pull out the oxygen that gets trapped in the water. So if the oxygen cannot dissolve in the water or be held in the water, then the fish could get very low oxygen levels and they could die. So this is particularly important in the Pacific Northwest because salmon are very affected by water temperatures. So they really like colder temperatures, and colder temperatures are going to contain a larger concentration of oxygen in the water. As the increased temperatures happen, they hold lower oxygen levels, and this can lead to fish kills in the rivers. So the effect of climate change may have a very dramatic effect on the ability of salmon to actually survive in this area. If our rivers continue to heat up, especially during their spawning seasons, they won't be able to traverse the long trek it's going to take so that they can reproduce in the upper stream beds where they normally are going to lay their eggs. They won't be able to make it because the oxygen concentration will be too low in the rivers to sustain them. Pressure also has an effect on solubility as well. And so we'll take a look here at something that's called Henry's Law. So pressure really is only going to affect dissolving gases inside of a liquid. So this is a gas-liquid combination. Liquid-liquid and solid-liquid solutions, pressure doesn't have much effect because the molecules are already so close together, you can't really get them much closer by increasing the pressure. But with the gas, you can, because the gas molecules, remember, are very far apart. Pressure has a big effect on the volume of the gases. So what happens is if you increase the pressure, you usually are going to increase the solubility of the gas inside the solution. This is what's done for your carbonated beverages. They're packaged under pressure so that you get lots of carbon dioxide inside your Pepsi solution so that you have very carbonated fizzy drink when you go ahead and open it up. So Henry's law states that the solubility of a gas is directly proportional to the partial pressure of the gas if the temperature is constant. So if you increase the pressure, you increase the solubility of the gas. Directly proportional. Increase, increase. So essentially, we can go back and explain why Henry's law works by using Le Chatelier's principle. So if you have your gas and you have your solvent, and this is going to go to your solution, your mixture of the two, if you have pressure increasing, pressure is going to be a positive input. It is essentially one of the reactants. And so if you increase this, it will shift or it will push your reaction towards the opposite side, towards the solution side. So when the system is stressed by increasing the pressure of the gas, more gas molecules are going to go into solution to relieve that increase in the pressure. When the pressure of gas is decreased, more gas molecules come out of solution and the reaction will go in the reverse direction. So there's a mathematical equation that can be used to determine the effect of the pressure on solubility. And so this again is Henry's law. And what it states is that the pressure of the gas is going to be directly proportional to the concentration of the gas in solution. And this is going to be related by a proportionality constant K. So what we can say is the concentration of one gas in solution at one pressure is going to be equal to the concentration of a second gas at a second pressure, and that's going to be related to this proportionality constant because we can set this equal to K, right? And so we saw with our other gas laws at the end of chapter 8 that we did similar things with pressure and temperature relationships as well, which were directly proportional. So if the partial pressure of a gas then over a solution changes while the temperature is constant, the new solubility of the gas can be easily found. So we can use this equation. And we'll do an example of this in our homework problems. So we'll stop here for this section.